Hi everyone. So I'm making a test video working with the blackboard instead of working with my iPad because I think it's actually more interactive for me to do that. And some of these ideas I think are easier to explain on the blackboard than they are to try to explain on the iPad because I can point to things and whatnot. So what I want to talk about today is branch cuts and Riemann surfaces, which is a way of taking multiple branches of an inverse function and gluing them together into a single function that is continuous. And we'll talk about what that means as we go. The motivating example here that I want to talk about is f of z is equal to z squared. And if you think about the polar representation of a complex number, one way of writing down what z squared is r squared e to the I 2t. So that is to say the squaring function squares the radius and doubles the argument of a complex number. And this function actually has two inverses. It has an inverse that you can think of as being the positive half of the complex parabola that this thing produces. And this undoes the negative values. And if you don't quite understand what I mean by that, think about the function f of x is equal to x squared, which is the regular old parabola. And the idea here is that each half of this parabola has its own inverse because this function is not one-to-one. So I can think about a function g1 of x, which is root x, and that's the inverse of this half of f. And then I have another function, g2 of x, which is minus root x, which you can think of as being the inverse that undoes this half of the parabola. And this isn't really a function. In fact, when you learn this in calculus, typically you learn it as this tipped over thing called x is equal to y squared. But thought of as a function of x, this is not an inverse because it's multi-valued. For each value of x, there are two values of y. So this is what's called a multi-valued function. And one way of thinking about it as a single object is to think of some way of gluing these pieces together. And that's what we're going to be studying here in the complex setting. Okay. All right. So again, remember, for the function z squared, we have two inverse functions corresponding to two different kinds of branches of the function that's being produced. And what we want to look at is the behavior of each of these branches of the inverse of z squared as they approach the place where the definition changes. And that's easiest to show you with a picture. Okay, so what we're going to do is we're going to look at the behavior of the function g1 and g2 as they approach this line. And notice that when I come from this side, I'm not actually allowed to use the number minus pi here in the argument of this function. And I'm not allowed to use the number minus pi here as well. So what we're going to do is we're going to try to draw a curve in the domain of g1 and a curve in the domain of g2. And we're going to see what happens to the limits of that curve as we approach this point right here where the function changes definition. So this line is called a branch cut. And it's a cut for reasons that should become obvious when we try to take a look at what's happening to the behavior of the function of root z when we approach that line from the top and from the bottom. So what I want you to imagine is that we have some arc in here. So you can just imagine we have a circle. And we're going to approach this branch cut from the top and the bottom. Now, z squared is an analytic function because it's a polynomial. So it has a power series, which is itself. And root z has a polynomial. It's an analytic function as well, as long as you stay away from negative real numbers. So by the extension theorem, this is also analytic, where it's defined. So what you should expect to happen, like any good polynomial, should be continuous. What we're going to look at what happens as we take this curve and we approach a point on this branch cut from the top and from the bottom, and we're going to look at the limits of what root z does to that curve. So if you were on some circle of a fixed radius, so suppose we have a fixed radius r, and I approach from the top, really what I'm doing here is I'm letting t go to pi, right? The angle, the argument of that function is approaching pi as I rotate in. And from the top, you should be able to see that for a fixed radius, this number approaches, so as t goes to pi, g1 of z tends to the number root r e to the I pi over 2, which is I root r. So as we approach from the top, we approach this value, I root r. So as we come in here, we approach I root r. What number do we approach as we come in from the bottom? If this function is going to be continuous, it had better be the case that these things match here, right? They should match. But notice what happens if you come in from the bottom. So from the bottom, you're taking t and you're letting the angle come into minus pi. That is, remember, the argument represents the angle in the unit circle. So as we rotate our radian angles around at 0, we go backwards towards minus pi. If I let t go to minus pi, and I plug that into this expression, I'm going to get a number that looks like g1 of z is equal to not I pi over 2, but minus I pi over 2. Root r e to the minus I pi over 2. And e to the minus I pi over 2 is like the cosine and sine. That corresponds to the angle on the unit circle corresponding to pi over 2 in the negative direction. And the point on the unit circle with coordinates, the coordinates of the point on that circle are 0 and minus I root r. So what are we saying here? We're saying that the limit of this function as I approach this point from two different positions, from the top and from the bottom, the limits are different. So the limit as t goes to pi of g1 of a number where we have a fixed radius and e to the it turns out to be equal to I root r. But if we come in from the bottom, g1 of r e to the it, we get minus I root r. Those aren't equal to each other. And what that means is the limits being different means this function is not continuous. It's not continuous at the branch cut. So this function is not continuous at the branch cut. So it's analytic everywhere it's defined, but we're not allowed to consider angles where we have to be really careful at this branch cut is what it means. We're not allowed to take curves and go across the branch cut with it. It's a barrier to thinking about what that function is doing. So an example of an illegal curve here I can't consider a curve that comes through the branch cut because that function is not continuous. So the definition of the function doesn't make any sense. As I approach from the top, as I approach from the bottom, I get different values. Okay, well that's frustrating. So what does the other branch do? So remember, the other branch has this pi in here. So the other branch of the square root function has this pi on the inside. Maybe we can compute its limit as we come into the branch cut, and we can see kind of how that looks. Well, so we're going to play the same game. As we'll think of a circle with a fixed radius, and we'll come into that branch cut from the top and the bottom. And here, as I let t approach pi, well, if you put that into this definition, you end up with g2 of r e to the it ends up approaching the number root r e to the I t over 2 plus, pi over 2 plus pi. Not legible at all. g2 of t is root r e to the I pi over 2 plus pi. And pi over 2 plus pi is 3 pi over 2. 3 pi over 2 corresponds to the point of the unit circle pointing down, which has coordinates 0 minus I. So this is minus I root r. So as we approach the branch cut from the top, we have minus I root r. And that looks familiar because that looks like how we approach from the bottom of the other function. So from the top and the bottom, surely that can't be a coincidence. What happens as we approach from the bottom? As t goes to minus pi, g2 of t is going to approach root r e to the I minus pi over 2 plus pi, but minus pi over 2 plus pi is pi over 2. This is I root r. And notice, from the top, this function approaches what this one does from the bottom. And from the bottom, this function approaches what this one does from the top. And so that gives us the idea that maybe we can think of the domain of these functions in a way that's going to let us blend them together, right? The idea is if I could somehow draw a curve where I transitioned, I can't draw that curve, but maybe I could draw this one. Maybe I could come into this line from the top using this definition of the function. And then if I want to go through the branch cut, maybe I could change the definition of the function to the second one, because this would be continuous. This point and that point match. These functions have continuous behavior at that point if I think about both definitions at the same time. And so the idea of a Riemann surface is to try to come up with a way of writing the domains of these two functions so that I can think about them as one function that's actually continuous at the branch cut. All right, so what I've drawn here is pictures of the domains of the two branches of the square root function. So here is the primary branch of the square root function, and here's the second branch. And the reason that we've coded the branch cut in two different ways, what I'm thinking about is cutting the domain along that line and sort of separating the domain out. And the idea that we should have noticed in the previous explanation is that if I drew a curve here in G1, it's not continuous if I go through this line, but the behavior of this curve on this domain matches the behavior of this curve on that one. And so the game that I'm going to want to play is to figure out a way to glue these things together so that if I drew a curve where I started at a point here and I rotated through this domain and approached this blue line, I need to set something up so I can switch definitions and come out of this blue line and travel inside this domain until it leaves through the orange line. Now this behavior and this behavior don't match, but this behavior matches this behavior. And so the idea that I've got is if I could somehow glue these two domains together, where if I go through the branch cut going this direction, I change from G1 to G2. And if I go through the branch cut going from G2 to G1, and I switch definitions the other direction, this gives me a way of thinking about both pieces at the same time. And not as a multi-valued function now, but as a single-valued function on a more complicated domain. And the way that we glue these two surfaces together, so to glue these to make the square root of z continuous at the branch cut. And that's going to be the sort of hard thing to draw, it turns out, is that I have to draw what the topological structure that does this. So that gluing, the surface that results from taking this and gluing it together with this, where we take this edge and glue it to that one, and this edge and glue it to that one, is called a Riemann surface. And I will try to draw one. All right, so this is a visualization of what a Riemann surface looks like. And what I want you to think here, what we've done is we've taken this domain of G1 and this domain of G2, and we're taking this edge of G1 and we've glued it to this edge of the domain of G2. And we've taken this edge of the domain of G2 and glued it to this domain, or this edge of the domain G1. And when we do that, we sort of get this self-intersecting surface, but this is the result. This object that we've drawn right here is the way of gluing these two things together so that this curve that I drew, where we start in one, and as we come around through the branch cut, we leave and enter the second domain as we go around. This is a way of thinking about both functions exhibiting the same behavior at the same time. If it's not clear how you travel on this surface, the idea is that you do it in a way that so you're continuous as you travel. So this circular path that I drew here in white, I'm going to draw it again on the surface over here. So the idea is that if you started on the branch cut, let's just say you approach the branch cut, you travel around the surface in a way that keeps you continuous. So we start here, we go up along the blue surface, and we travel, and as we come through, now we're flat, we're not tipped up anymore. So when I pass through the branch cut, I need to make sure that I pass through to the lower branch. So you can imagine that now we're behind and we scroll through like this, and then we pop out, and then we come back up to the branch cut. Now I rejoin the original surface here. So this curve you can think of as traveling up and around through the branch cut onto the lower sheet, around the lower sheet, and then back up to the branch cut and up onto the upper sheet again. So this twisting loop here is the same thing that I've drawn where I drew this path here in two pieces. I start on the upper sheet and I travel in a circle. I pass through to the lower sheet and I travel in a circle and I return. And that's what I've tried to simulate here. Okay? The reason that you do this is because on the Riemann surface, f of z is equal to square root z is continuous everywhere. So as I pass through the branch cut, it tells me the way to shift the definition of the function. So you can think about the Riemann surface as sort of representing like a multi-part definition of a function that accounts for the fact that I have this, this line that I've got to be really careful of. Okay, so that was my test video. We'll see how that goes.